After studying this module, you will be able to understand various tests for testing the stationarity of a series. Also would be able to understand autocorrelation function and its statistical significance. I am sure you would also learn about the different QE statistics to test the stationarity of a series. After introducing the concepts of stationarity and its importance in the previous modules, it becomes important to know the measures to test the stationarity of a time series. That is, I am sure you would be interested to know how are we sure that whether a series has stationarity or not. It is therefore important to test for the stationarity of a time series due to many following reasons. First, the property of a stationarity in a time series has a major impact on the behavior and properties of a time series. If a series is a non-stationary one, then the persistence of shocks will be infinite, hence leading to wrong estimation of the terms. In contrast, in a stationary time series, the shocks decline to 0 over time. Non-stationarity in a time series can lead to the problem of spurious regression. By spurious regression, we mean that even though the variables are unrelated, the R square may still be very high. The reason for understanding the properties of stationarity is also because in the case of a non-stationary time series, the standard OLS assumption of asymptotic analysis will become invalid. In simple words, T ratios will not follow T distribution and thus we cannot test the hypothesis efficiently. Let us look at these testing first from the graphical point of view in this section on graphical analysis. Graphical analysis is one of the simplest ways to test the stationarity of a series by merely looking at it. A graph can depict whether the time series is stationary or not if its mean remains constant over the period of time. If the mean is variable over time, it would imply that the series is non-stationary in nature. For example, if a variable, say GDP, has an upward trend over a period of time, this may imply that the mean of GDP is variable. This means that the series is non-stationary in nature. Graphically, the stationary and non-stationary series are depicted as follows. First, the stationary series. As we all know that by the term stationary, we mean that the mean and variance is constant over time. So, graphically, we can depict the stationarity of a series by merely looking at it and seeing a trend in the movement of the variable. For example, in our figure 1, it is clearly visible that the variable yt is showing a constant trend in its movement, thus implying constant mean and variance. In simple words, observations are fluctuating around a mean only. Thus, from the figure we can conclude that yt is a stationary series. I am sure you can see we have time on the x-axis in this figure and we have the value of yt on the y-axis. We can see ups and downs, but by and large, if you look at the means, the values or the yt values, they oscillate around yt equal to 10. The second series is defined as non-stationary time series. By the term non-stationary time series, we mean therefore that the mean and variance are not constant throughout the series. Thus, the series would show either a rising or a falling trend, implying that the mean and variance are changing throughout the time series. We can show this phenomena in figure 2, where the variable yt is showing an upward trend, implying that the variance and mean are not constant and instead are continuously rising. Therefore, we can conclude that the series yt is a non-stationary time series as depicted in this figure 2, where again we have time on the x-axis and yt on the y-axis. But I am sure now you can see that how the series is moving up and down, but there is an upward trend over the time period in this series, and the mean therefore is increasing, and there is a likelihood that even the variance may be changing over the period. We can therefore conclude from this that the graphical test is one of the easiest methods to judge the stationarity of a series. If the graph shows a constant trend, it implies that the series taken into consideration is a stationary time series. On the other hand, if the graph shows an increasing, decreasing, or even an haphazard trend, it implies that series is non-stationary time series. However, there is a problem in this graphic method, and that problem is that it is just an indicative method. One is never sure. It is not a confirmatory kind of a test. Let us look at some of the confirmatory tests, where we begin first with autocorrelation function. This is another simple test of stationarity and is known as autocorrelation function. However, first let's introduce the concept of autocorrelation in brief. Autocorrelation means that the error terms are related to each other over time, or in other words, the value of the error term in one period is correlated with its value in another period. Because here when we say autocorrelation, auto means self, and therefore the series is related with its self values, maybe of different time periods. So in this case, they are said to be serially correlated or autocorrelated. Now, due to the presence of autocorrelation, the OLS estimators are no longer efficient. That is, they are no longer blue, which is best linear unbiased estimator. But they would still remain unbiased and consistent. So the main causality is of efficiency. Autocorrelation is broadly of the following types. For example, we may have spatial autocorrelation or serial autocorrelation. The diagram clearly shows that autocorrelation can be divided into two categories: the spatial autocorrelation, which means correlation between cross-sectional units, and serial autocorrelation, which is correlation amongst terms over a period of time. In spatial autocorrelation, there is correlation between the cross-sectional units, while in serial autocorrelation, there is correlation amongst the terms over a period of time. The question therefore which arises and which we must try to answer is that what are the reasons for autocorrelation? Let's try to understand some of these reasons here. The reasons for autocorrelation are as follows. First, over the period of time, the data shows a common trend. Therefore, autocorrelation becomes more prevalent in a time series data. The second reason could be of specification bias, which is one of the major reasons for autocorrelation. Such kind of autocorrelation is known as quasi-autocorrelation. The third reason is that autocorrelation may be caused due to the incorrect functional form used for the time series. Misspecification of a variable may also lead to autocorrelation. We may also have autocorrelation due to data transformation, which may cause the terms in a series to be autocorrelated. lags in a variable are one of the most important reasons for autocorrelation. Also, non-stationarity of a series may lead to the problem of autocorrelation. Therefore, to avoid the problem of autocorrelation, a series needs to be fitted into a correct functional form and should be stationary. Let us now try to understand and define autocorrelation function, ACF. ACF is one of the simplest ways to test stationarity of a series. It can be calculated using a simple formula given as that rho k is equal to gamma k upon gamma 0, where rho k is the autocorrelation function at lag k, gamma k is covariance at lag k, and gamma 0 is variance. It is important to note that if in the above equation the lag operator k becomes equal to 0, the covariance becomes equal to variance, and hence rho k becomes equal to 1 because numerator, which is gamma k, is equal to gamma 0. Now similarly we can see that the covariance and variances are measured in the same units. Therefore, rho k is just a pure number with no units of measurement. As we have said, the unit of measurement of the numerator rho k, gamma k is same as the units of the denominator gamma 0. The main practical question is about choosing the length of the lag k, that how do we decide what should be this k. A rule of thumb is to compute ACF up to 1/4 to 1/3 of the length of the time series, which means, for example, if we have 2335 observations, 1/4 of this would be almost 589 lags. We will not show the ACF at all these lags, but consider only the first 30 lags. We can test the statistical significance or significant of each autocorrelation coefficient by computing its standard error. The statistician Bartlett has shown that if a time series is purely random, the sample autocorrelation function rho k follows normal distribution with zero mean and is expressed as, we are saying in that case rho k would be distributed normally n with mean 0 and variance 1 by n. In order to detect the type of time series model from looking at the ACF, following key points they need to be kept in mind. First, if the time series is ARP, ACF is infinite and it damps out. If time series is MAQ, then ACF is finite, it cuts off after lag Q. If the time series is ARMA, then ACF is infinite again, however it damps out. So in practice, however, we can compute sample autocorrelation function SSCF only because the population is not known to us. To compute SSCF, we first compute sample covariance and sample variance. Sample covariance can be calculated using our simple formula, which is that sample covariance is equal to sigma yt minus y bar into sigma yt plus k minus y bar divided by n. Similarly, sample variance is equal to sigma yt minus y bar whole square divided by n. Let's also define sample autocorrelation function as equal to sample covariance upon sample variance. So once we calculate sample covariance and sample variance, we can easily find out sample autocorrelation function. So if we now plot the sample autocorrelation function on a graph, it will be termed as sample correlogram. So what is a correlogram? Let's discuss that correlogram. It is an aid to interpret a set of autocorrelation coefficients through the medium of a graph. it is generally used to get a basic understanding about the time series on the following aspects, which are, one is the random data, second is to observe time series white noise term, then to observe whether a time series is autoregressive in nature. In addition, correlograms are used in the model, and we have the identification stage for Box-Jenkins-Irma time series models. Autocorrelations should be near 0 for randomness. If we do not check for randomness, then the validity of many of these statistical conclusions becomes suspect. The correlogram is an excellent way of checking for such randomness. Let us, students, now try to discuss and understand the properties of correlogram. Correlogram is not a function of time, rather it is a function of lag length which ceases to grow and decay after a particular time. So let's look at a correlogram in the diagram where we have the lag length on the x-axis and autocorrelation function, let's say sample autocorrelation function on the y-axis. And we have these different points which are joined and we get a correlogram. Now, what we've observed is that this row k, we are assuming is distributed normally with mean 0 and variance 1 by n. At 95% confidence interval, the limits would therefore become rho k plus minus 1.96 into 1 upon under root n. This gives us the confidence interval at 95%. I am sure you would all know at 95% the value of Z alpha by 2 is 1.96. We can see that in figure 3 it is visible that the fluctuations are getting dampened towards the end slowly. This implies that the series is non-stationary in nature. However, if the graph would have shown a constant trend, then it would have implied a random walk model. To summarize, in case of a stationary time series, the correlogram dampens towards the end quickly, while for a non-stationary time series, it dampens slowly. In case of a pure random series, the autocorrelations at all legs is equal to 0. Let's look at the Box-Peirce-Q statistics. Box and Peirce Q statistics was formulated in the year 1970 to test the null hypothesis that the first set of k autocorrelations of a stationary time series comes out to be 0. Box-Peirce-Q statistics is a test which indicates that if the residuals are white noise, then the Q statistics follows a chi-square distribution. Therefore, we can calculate the Q statistics as follows. Q is defined to be equal to n sigma rho k square, where sigma ranges from k equal to 1 to m. And this is distributed as chi-square with the m degrees of freedom. So rho k we are saying is sample autocorrelation with lag k, m is the number of lags to be tested. So if the calculated value of chi-square is less than the table value, then we accept the null hypothesis stating first set of k autocorrelation comes out to be 0, hence implying that stationarity exists, else the series would be non-stationary. Let us now move on to Elson Box Q statistics. Elson Box Q statistics is the new and modified version of Box-Peirce-Q statistics, and therefore the test statistic obtained from it known as the modified Q. The test was formulated by Greta M. Elson and George E. P. Box. It is a statistical tool to test whether autocorrelations in a time series are different from 0 or not. It tests the overall randomness of the legs. To apply this test, we first take the null and alternative hypothesis as follows. Null hypothesis S0 is defined to be where the data is independently distributed, that is, correlation is equal to 0. The alternative hypothesis H1 is defined as the data is not independently distributed. The test statistics for Elson Box test is as follows. LB is equal to n into n plus 2 sigma rho k square upon n minus k. Sigma varies from k equal to 1 to m and is distributed as chi square m, where n is the sample size, rho k is the sample autocorrelation with lag k, m is the number of lags to be tested. If calculated value of chi square is less than the table value, then stationarity exists, else the series would be non-stationary. So after doing all this, let us now summarize. So as a summary, I may say that we have learned that the graphical method of testing stationarity is one of the simplest methods. In case of a stationary time series, the endogenous variable will show a constant movement throughout the time series or time period. In the non-stationary time series, the endogenous variable will either show an increasing or decreasing trend over the time period. We have also learned that autocorrelation means that the error terms are related to each other over time, or in other words, error term in one period is correlated with its value in another period. Then they are said to be serially correlated or autocorrelated. Autocorrelation is of two types. Firstly, the spatial correlation, in which the correlation exists among the cross-sectional units. Secondly, serial correlation, in which correlation exists over a period of time. We have also learned how autocorrelation can be calculated using the formula rho k is equal to gamma k upon gamma 0. In simple words, it is the ratio of covariance with lag k and variance, and is known as the correlation coefficient. A correlogram of a time series is a test to determine the stationarity of a time series. It is the graph of autocorrelation, keeping in view the lags taken into consideration. In case of a stationary time series, the correlogram dampens towards the ends quickly, while for non-stationary time series, it dampens slowly. In case of a pure random series, the autocorrelations at all legs are equal to 0.